Give me just a minute here. Okay, hi everyone. Thanks for your patience. Sorry, I was looking over the labs that are, or the lab that's due for this week. You've got two different things going on. We're working on nuclear chemistry. And the first part is in your lab manual. So you'll take a picture, you know, as you've been doing it, work on the lab manual, take a picture, blah, blah, blah. The second part of it though is a dry lab that we like to offer that we may end up doing some work on ourselves. So you'll need to print it off or if you have like an Adobe and you can just write on it on your computer, that's fine as well. You can open it as an Adobe file and just save your annotations on it. So let me share my screen and I'll show you where that lab is. So in the, if you click on the all procedures here, it'll tell you that it's in like a folder. I actually just put it right here. Okay, so your lab 8, you've got your nuclear chemistry, you'll turn 2 things into that. You'll submit actually 2 labs. So it'll be the one out of the lab manual. And the second thing will be this nuclear radiation dry lab. So if you click on this thing, it should open it as a PDF sort of plugin to your Moodle, or you can open it in a separate tab like this. And then from here, you should be able to add notes. So I can write, you know, what an alpha particle is and a gamma particle. I can write my symbols and things like that. Okay. So we will be doing a little bit of work with this as well. So let's go back. We'll use the slides, guide us through this, doing some example problems too. So nuclear chemistry sounds a little scarier than it is. I mean, nuclear chemistry is a very complicated thing, but as far as what you guys are going to be working with, we'll keep it pretty simple. Okay, so here's a dude. He's going in to get some radiation work done, probably to scan to see if there is any sort of abnormalities. It looks like they're working with his head. So they're using a radioactive technology that emits gamma radiation. So it's not something you want to be exposed to on a regular basis, but every now and then, and you can use that and it will scan the body for irregularities. All right, so radioactivity. So let's talk about natural radioactivity. So here we have an isotope of iodine. Let's remember our isotope stuff, right? So we've got our symbol. In the lower left-hand corner, we have our number of protons, which sort of, I mean, these two values here correlate to each other, right? If it's iodine, it always has to have a symbol or atomic number of 53. That's what defines iodine as iodine. And then in the upper left-hand corner, that's the number that can change. That's our atomic, or rather our mass number. Our mass number is going to be the number of protons plus the number of neutrons. So if we have, let's say we have a heavier isotope, we're going to increase the number of neutrons. If we have a lighter isotope, we're going to decrease the number of neutrons. Isotopes correlate to radioactive stuff. Certain isotopes are radioactive or they're more unstable. Other ones can be stable. Just a second here. Sorry, folks, I'm just getting myself set up a little bit late here. I just want to make sure I have my notes open so I don't forget to mention anything outside of these slides that we want. They're just taking me forever. Lauren, it is totally okay if you print out the dry lab and then scan it. Yeah, I know sometimes people may not have access to printers. That's why I said you can just do it through your computer. But if you do have access to a printer and you're more comfortable printing it out and writing it on paper, that is completely fine. And then scanning that in, yeah. Okay, so yeah, so let's continue here. So elements that have an atomic number of 20 or higher. So the bigger the nucleus gets, the more chance there is for instability in the nucleus. So things that have an atomic number of 20 or higher, which is around calcium, usually have one or more unstable isotopes, or situations where the nucleus is unstable. It kind of starts to almost disintegrate or fall apart. That doesn't mean that things that are smaller than 20 can't have unstable nuclei as well. So carbon 14, carbon Carbon has an atomic number of 6, so it's a small nucleus, but it actually is unstable. So what happens is that when we get these nuclei that are sort of hunky, they're packed with like a lot of neutrons, or they're really, really big. They're unstable, and they are what's known as radioactive, which means that they're going to try and emit small particles of energy that are called radiation in order to become more stable. So they may like give off some alpha particles, or they may give off a beta particle or a positron, and we'll talk about what each one of these is. Sometimes they don't even give off matter, they just give off energy as a gamma ray. And what this does is it helps to lead to a more stable nucleus. So any isotope that will emit radiation, we say is a radioisotope. It will, when radiation is emitted, it may undergo a change in the number of protons. And it actually may convert, because we're changing protons, it can actually convert into a different element. So remember back in chemical reactions, we always said, hey, the stuff you start with equals the stuff you end with, right? If you've got 3 aluminums, you better have 3 aluminums at the end. That is not the case when we're dealing with nuclear chemistry. With nuclear chemistry, we can start with aluminum and actually change into a lighter element. So be okay with being able to convert into new elements here. So atomic isotopes or atomic symbols for various isotopes are often written like this, but sometimes they can be written like this or like this, right? So if we're dealing with iodine 131, and we wouldn't call it iodine 53, because iodine 53 is the number of protons in order to be identified as iodine. But we would call it iodine 131, meaning that we have a total nucleus mass of 131. Sometimes they write it as iodine dash 131, or they'll write it as the symbol iodine with the 131 after it. Okay, so just a couple different ways we can see this. Here are some more ways that we can see things. And also this is looking at, well, actually this one is looking at stable isotopes versus radioactive isotopes, and then also some ways that they can be written. So stable isotope for magnesium, 12 protons. This is specifically magnesium 24. So this is a situation where we have 12 protons, and then we also have 12 neutrons, right? Because 12 plus 12 gives us the 24. We can also see it written as magnesium 24. When we say that it's a stable isotope, what we mean is that it's not going to decay. This nucleus of 12 protons and 12 neutrons is stable. It likes its formation. So it's not going to deteriorate or break down into something else. Now, there are radioactive isotopes of magnesium. Magnesium 23 is an example of a radioactive isotope. There are 12 protons, but there's only 11 neutrons. And this, for whatever reason, is not a stable configuration for magnesium. So it will want to decay to something else. Magnesium 27 is also a situation where we have a radioactive isotope. I don't expect you to have all the stable versus unstable radioactive stuff memorized, okay? So I don't expect you to go through the periodic chart and be like, nickel has 3 radioactive isotopes. Wouldn't do that. Here are some other ones. So iodine does have 1 stable isotope. So iodine 27 doesn't decay, but the other iodines, iodine 25 and iodine 31, will decay. So this is sort of its happy spot. And then if it deviates from this happy nucleus, it becomes unstable. Uranium, kind of one of those elements we think of being radioactive or unstable, right? It doesn't actually have any stable isotopes. There is no stable uranium. Any uranium that's out there is going to decay. Okay, so we've got uranium 235 and there's also uranium 238, both of these being unstable. So how do these things become stable, right? Like if these things here down here are unstable, they need to make some sort of change in order to become a more stable version of themselves. And so the first way that something can become stable is through alpha radiation, okay? Alpha radiation, or an alpha particle, is pretty much a helium 4 atom all right, but it's going to be 2 protons and 2 neutrons, all right, just identical to a helium nucleus, and it's got a 2+ charge that's emitted. We also have this thing called a beta particle, and so the alpha particle has this little symbol here, alpha, and I'm just gonna, oh, come on, slides. I'm going to hop back over here. So on this chart here, we can see alpha, beta, and gamma radiation. So you can fill those in there, the different types of radiations. So alpha is sort of the clunkiest of the radiations. It's a pretty big particle. I mean, a helium, that's pretty large. Beta, or this little like italicized B particle, is a high energy electron with a charge of -1. Okay? This forms when a neutron is actually converted into a proton. What? Yeah, we can do that. Okay, so we take a neutron, which normally has a neutral charge, and this is the symbol for a neutron. And let's talk a minute about these symbols. So here's one. We've got helium. I put a 2 in the lower left-hand corner. This is talking about the atomic number. And the top number is talking about the mass total. All right, or another way to think about it is that this number down here is protons. And this number down here is protons plus neutrons. Okay, and then we've got our symbol. So this would be our symbol for an alpha particle. We write helium because it is helium. It's got 2 protons, and then it's got a total of 4 protons and neutrons, or 2 protons and 2 neutrons. The beta particle, which is a high energy electron, we're going to write like this. So we write a little e, and then we're going to write on the lower left-hand corner, this is talking about the number of protons we have. Well, we have a -1. We have the opposite of a proton, right? A proton would be 1 or a positive. This is going to be a -1. So this is inferring that we have an opposite charge. What do I put in the upper corner? The upper corner is going to be a 0. Why is this upper corner 0? Because our total mass, this is the total mass, is 0. Remember, an electron doesn't hold any mass. It just holds a charge. So it's kind of a funkier way of thinking about an electron. So our symbol for electron will look like this. E with a 0 on the top, symbolizing no mass, and a -1 in the lower left to symbolize that it's a negative charge, or the opposite of a proton. So how we get this electron to come off of our nucleus, and I want to make this clear, this electron is not coming off of the atom as a whole. Okay, so it's not, we've got our nucleus in the center, and then we've got our electrons around here. The electron is not falling off from the outer shell. It's actually coming from a conversion of a proton, or rather a neutron, to a proton. So when we form a proton here, the electron comes off of there. Okay, so we're not going to be down an electron on the outside. So here we go. We've got our neutron, and we convert it to a proton. Here's my proton, and you may be thinking, well, that's not a proton, that's hydrogen. Isn't that H? Well, hydrogen without an electron is just a proton. Because let's do the formula for hydrogen. So hydrogen has a proton in the center, the proton, and it's got an electron floating around it. There are no neutrons in this. So if I get rid of my electron, what am I left with? I'm just a proton. That's why they call it that. Okay. So we've got a hydrogen. The lower left-hand corner tells me how many protons I have, 1 proton. The upper left-hand corner tells me how many I have in total. So I have protons and neutrons. I also have 1, so there are no neutrons here. And I give off this electron. And we'll talk more about this, but when looking at these nuclear equations, the stuff, we sort of separate ourselves at the arrow. The stuff on the top has to equal the stuff on the top both sides. That's how we balance here. So if I have a 1 on top here, there's a 1 on top. This plus this also needs to equal 1. Okay. What do I have on the bottom for my neutron? I have a 0, right? So this plus this has to equal 0. A 1 plus a -1 does in fact equal 0. So those are balanced out. We'll do a bunch of practice with those in a little bit. But that is the gist of it, is that the total mass needs to equal on the top, and the total number of protons / negative proton charges have to equal each other on the bottom. Okay. Let's go to the next type of thing. Okay, so I have a positron, which sounds very sci-fi-ish. If it's a real deal thing, you have your little beta symbol with a plus. This is an example of antimatter. This is the symbol here. So a positron is like an electron in that it has no mass, and it's like a proton in that it has a positive charge. So it's like the opposite of an electron. So our symbol for that is going to be an E. We won't have any mass because these like electrons don't have masses, but we will have a positive charge. How do we get a positron? A positron happens when we take a proton and we convert it into a neutron. So if I have a proton here, which is H with a 1 and a 1, and I convert it into a neutron, that means I need to take what was a proton and I've got to ditch its charge. I don't want to ditch its mass. I want to keep its mass, but I want to get rid of its charge. How do I get rid of the charge? I kind of poop out a positron. So we've got alpha decay, beta decay, positron decay. And then the last type of decay we have is known as a gamma ray or gamma radiation. This is the highest energy radiation out there. Right? This is released from the nucleus when it decays. And the important thing about this is that there is no mass to it. It happens when we have the release of a beta particle and a positron, right? No mass, negative charge, positive charge. This is when matter and antimatter come together, and we end up getting this guy right here. So we convert these two particles into just pure energy. So the symbol for this is going to be this sort of curly Y. The charge on it is 0, and the mass on it is 0. And so it's important with all these little symbols to know what the charges on these things are, how many protons, how many neutrons, how many electrons, and this is sort of all summed up in the next page. So let's look at that. So here I've got my alpha particle, and my alpha particle will be written like this. There is an inferred 2+ here, okay? Because there are no electrons in this. It's just 2 protons and 2 neutrons. So the 2+ isn't written in there, but this is where we have 2 protons and 2 neutrons that are emitted in a little packet. The mass number on this thing is 4 for the 2 protons and 2 neutrons. The charge on it is +2, right? If you have 2 protons and you don't have 2 electrons to counteract it, you'll have a positive charge. This is the biggest, clunkiest of the emissions. The next one we have is that beta particle. So there's our little symbol, and this is just a high energy electron. So when we have our high energy electron, why does this thing come out? It's because we're taking a neutron and converting it to a proton. So we're taking the neutral charge and we're sort of removing some charge from it to get to a positive charge, or removing some electrical charge to a negative electron charge to get to this positive proton. The mass on this thing is 0 and the charge is -1. So that lower part, you can sort of think of it as the amount of positivity. This has a 2 positive charge, or 2 protons. This has an anti-proton or a minus charge. A positron is that antimatter. That's when we are going from a proton to a neutron. This is neutron to proton. This is proton to neutron. If we're going from a proton to a neutron, we have to get rid of some of that positive charge. The mass on this thing is still 0, so it's still kind of like an electron, but instead of it having a negative charge, it has a positive charge. Then we have our gamma ray, which is when we just are emitting pretty much pure energy. So we've got our symbol, our little curvy Y, and it's a 0, 0. So it doesn't have any mass and it doesn't have any charge, which sounds super out there, right? Is it anything? Yes, it is actually something. It's pure energy. It's a very, very high energy ray. So energy is lost to help stabilize the nucleus. Couple other ones that you want to know, the proton is, it directly coincides with the hydrogen, right? So you'll see these used interchangeably. Sometimes we write it as the hydrogen with a 1, 1. Sometimes we write it as the symbol P. And then what's a neutron? It's that lowercase cursive n. And then sometimes we write it with the actual numbers in place. So a neutron doesn't have a proton. It has no charge, but it does have mass of 1. And we can see that happening over here. There's a 1 and a 0 for the charge, which is congruent with what you know about a neutron, right? It has mass, but no charge. So we want to be able to work with, use, manipulate all these symbols. They are definitely different than anything that y'all have done thus far in your chemistry. Okay, if you've taken 092, you haven't seen this. Some high school chemistries will go over nuclear chemistry, but usually not, right? It usually doesn't happen until your Gen Chem 1. So give the name and symbol for the following types of radiation. So alpha radiation is going to give off what type of particle? Well, alpha radiation is going to give us an alpha particle. All right, so we've got an alpha particle. And what is an alpha particle? An alpha particle is just going to be synonymous with a helium. So we write helium with the 4 and the 2. Okay, I popped them up. Okay, radiation with a mass number of 0 and an atomic number of +1. So if I have a mass number of 0, that's my top value. A +1 is my atomic number. We're going to say that that thing is, in fact, a positron. This is a positron. Oops, sorry. And if you're wondering, well, if it has a +1, isn't that a proton? That's super common for people to think, but remember, in order for it to be a proton, it has to have mass as well, right? This says that it has a mass number of 0. So this here is a positron. What does a proton look like? Well, a proton will have a 1 in that lower left-hand corner, a +1, but it'll also have a 1 for its mass. This would be a proton. Okay, so these two things are different in that this has no mass, this does have a mass. Radiation that represents high energy radiation released from the nucleus, that's going to be our gamma. No mass, no charge, pure energy. Okay, so moving on. So a lot of times when we hear radiation, we think, ooh, that sounds scary, right? I don't want to be around a bunch of radiation. Well, why is that the case? Because when radiation hits molecules, it can actually knock away electrons and make the whole molecule relatively unstable. One thing that it can do is it can knock away electrons from your water molecule, giving you this thing called H2O with a positive charge. So it's water, but with 1 less electron, which can cause bad chemical reactions. So things that can happen, cells most sensitive to radiation are those that undergo rapid cell division. So anything that has like a quick turnover, like bone marrow, skin, reproductive cells, cancer cells. These are things that do not like radiation, okay? Because if the radiation gets into those things, it can have an effect right before it divides, the cell divides, and then you have this sort of overgrowth of irregularity or instability. So we do want to try to protect ourselves from radiation. As far as how radiation goes, the bigger the particle, the clunkier the particle, the less damaging it is. All right. The smaller it gets, the higher energy it gets, the more damaging it is. So alpha particles, and remember, an alpha particle is just a big helium. That is relatively harmless. It can be stopped by paper or clothing. It's not going to do much. Okay. If we're dealing with a little bit of a smaller particle, like a beta particle, which is again just a high energy electron, that can be stopped by lab coat and gloves. A gamma ray, so highest energy, which is, remember, it's no mass and it's no charge, it's just pure energy. This will be stopped by something like a lead shield or concrete. So that's why they tend to put nuclear reactors behind like big amounts of lead and or big concrete structures. Or if we're disposing of radioactive material, it needs to be disposed of properly in a situation where we have a really thick rock wall or thick concrete wall or a lead container. Other ways to protect yourself from radiation: limiting the amount of time spent near a radioactive source. The more time you spend by radioactive material, the worse off it is. So people who have spent large amounts of time around like power plants that have leaked tend to have more damaging effects than people that, you know, went in, did some research and left. And then also increasing the distance from the source. So people who were very, very close to Chernobyl, which was a radioactive explosion that happened in Russia, had much worse effects than people who were, say, in the United States. You can, when you do have something like a nuclear fallout from a nuclear blast or a radioactive meltdown from a nuclear power plant, you do get this fallout across the whole globe. We can actually find, like in our rock records and our soil records, we can see spikes where we did a lot of nuclear testing. So you do find it all over the place. It just isn't deadly when you've moved, you know, say half a turn around the globe. But when you're right next to the source, it can be pretty damaging. So if you happen to be working in a field where you use radioactive material, you want to try to keep the time you spend near that material limited. Okay. So if anyone's going to become like a radiologist or something like that, you will be given the proper equipment to keep yourself safe. That will include, you know, lead-lined coats and things like that. And then also you will be in a room. So that is separate from wherever the equipment is. So again, alpha particles, you can stop with a piece of paper. This isn't too damaging. Definitely gets more as we move into gamma. So this here, what type of radiation will be blocked by each of the following? So lead shield will block all radiation. It doesn't just block gamma. It will also block beta, and it will also block alpha. Paper and clothing can block alpha. If the clothing is hardy enough, like let's say it's a really durable material, tightly woven, more like a lab coat, you might be able to stop beta as well. But in this, it's saying alpha. So it depends on the clothing. So I had sort of touched on nuclear reactions, but we're going to get into those again and in more detail. So here is an example of nuclear radiation or nuclear decay. So I have uranium-238, and it's this big clunky, it's got this big clunky nucleus, right? Lots of particles in there. It's unstable. So what it wants to do is it wants to decay to what's known as a daughter isotope. So this we call the parent isotope. Sometimes they call it the father isotope. The parent isotope is the unstable thing or the starting thing. So it will decay, and specifically this one will decay to thorium-234. So we'll put our symbol thorium, always has an atomic number of 90 and 234. This thing is stable. In order to do this, in order to become this new thing, it has to shoot off an alpha particle. And this alpha particle that's come off, combined with the thorium, the number of the mass and the charges for these needs to total the initial. So here I had a number of 238 on the top. So the combination of 4 and 234 needs to total that 238. The same thing is true for the mass or the charge proton number on the bottom. 92 on the bottom. So my 2 here and my 90 here need to equal that. 90 plus 2 gives me that 92. One way that I could write this out, obviously I wouldn't have you guys drawing those elaborate pictures every time, but we would write our symbol. So we're starting with the 238, 92 uranium. We're going to decay into the thorium, 234, 90, plus the alpha particle, 4, 2, helium. And to make sure that this thing is balanced, you want to look at this value here, make sure that equals all the components over here. It does. 92 down here, we got 90 and 2. Okay, so that's in your nuclear equation, that has to equal. It doesn't have anything to do with, hey, I've got a uranium on this side, so I need to have a uranium on the other side. That is not the case with nuclear chemistry. So here's another one. In a balanced nuclear equation, again, particles are emitted from the nucleus. The mass number and the atomic number may change, but the sums of them need to equal each other. So my mass number up on top here, I've got CF, and it's going to decay to CM and an alpha particle. My CF has a total mass of 251. That means that my other side, everything on this side, needs to also equal the 251. Same thing here, I've got an atomic number of 98. So the total on this side of my bottoms need to be 98 as well. So 247 plus 4 does give me the 251. And then 96 plus the 2 gives me the 98. So those are balanced and those are balanced. This is a correct formula. So hopefully now you can start to see that, hey, what if I was to give you this and say it underwent alpha decay? Write a formula for it. You should be able to do that. Why? Because you know what you're starting with and you know one of the things you're ending with. So everything else, you just go through subtraction. So let's actually, well, let's look at another example of this. So anytime you undergo alpha decay, like if I say, hey, I've got uranium-238 and we underwent alpha decay, well, you better give off an alpha particle. And then everything that remains is going to have an atomic mass that's decreased by 4 and an atomic number that's decreased by 2. And then you just work backwards to figure out what the symbol is. Right, so if I have 238 and I say it's undergone alpha decay, you're going to write your alpha particle. Then you're going to write a second nucleus or a new nucleus that's going to have a atomic number that's 2 less than your starting and an atomic mass that's 4 less. And then you can figure out the symbol by, well, looking up what 90 is on the periodic chart, which is TH, thorium. So write an incomplete nuclear, how do we go to write these equations? So write an incomplete nuclear equation, determine the missing mass number, determine the missing atomic number, determine the symbol, and then write the equation. So let's do Americum 241. I'm gonna do this over here. Okay, so we have Americum 241. And I don't know if you're on my period. 95, okay. And this undergoes alpha decay. And so I'm saying, let's write a balanced chemical, or not, rewind. Let's write a balanced nuclear equation for this. So we start with our given thing. We've got Americum 241. If I undergo alpha decay, that means I'm undergoing a change. So I'm going to put my arrow. And I know one of the things has to be an alpha particle because it's undergoing alpha decay. So right off the bat, I like to write my alphas first. A lot of times in the text, they'll write it second, but I like to write it first. So I've got a 4, a 2, and an HE, right? That is alpha. That's just what it is. Now I have to write what the remaining nucleus is. So I don't know what the symbol is yet, but I can work from this information, subtract this to get our numbers there. So if I'm at 95, this total side here also has to be 95 on the bottom. So 95 minus 2 will give me 93, correct? 93 plus 2 gives me the total 95. On this side, right, 241 here, that means this needs to be 241 as well. So subtract the 4 and we get 230, where am I? 237. Is that making sense where those numbers came from? And I'm not just pulling those out of thin air. It's just a real basic addition subtraction. So whatever this is, these two numbers have to add up to be that. So this is 93, 2 gives me the 95. This is, I don't know why I have it as 337. This is 237 plus 4 gives me the 241. Now I have to write a symbol. So go to your periodic chart and find number 93. That's what, Neptunium, NP. So now I have this nice balanced nuclear equation. I'm going to clean it up a little bit. This is what it means when Americum undergoes alpha decay to become Neptunium 237. We'll do another example of this, but does anybody have any questions on like where those numbers are coming from? If you're thinking this seems kind of easy, it's right, it's just basic subtraction addition. It is relatively easy. Let's look at the one of the ones from the worksheet from the homework. Okay, so you may want to asterisk this so you can fill it in later. I'm gonna skip forward here. Okay, so we're looking at this one. Let me zoom in. I'm not going to do all of them, but let's just do this first one. We've got what, polonium. So write a balanced nuclear equation for the alpha decay for each of the following. We're just going to do A. Okay, so we've got polonium 84. Rather, it's polonium 208, but it's polonium. We put the 84 in the lower left and then the 208 on the top. So polonium 208. So I want you to write a nuclear equation where you alpha decay. So I'd start with an arrow and an alpha particle and then work from there. you just another minute on this one. All right, so when looking at this, and for every one of these, when you do go back and do them, they're all sort of repetitive and that they're all going to get an arrow and they're all going to get an alpha particle. Okay, every single one is getting an alpha decay in this section. So now I've got to figure out what's left over. Well, if I have 84 over here, that means this plus whatever this value down here is for this nucleus needs to equal 84. So I'm going to put in 82 there. 82 plus 2 gives me 84. Those are balanced. Now I do the same thing with the top. So I've got 208 here and I've got 4 of it being occupied here. So I'm going to make this 204. 204 plus 4 gives me 208. So we're good there. Now we need to write our symbol. So we go to our periodic chart and we see what is 82. And I'm looking, oh, lead, okay. PB, 82. Yes, no, maybe so. Yeah, it's not too bad. I don't think it's too bad. As long as you remember what your particles are. All right, so let's look at some other types of decay. Oh gosh, clear this. So we've got our beta decay. So remember, a beta particle is just an electron, the high energy electron. So this is what this symbol is going to look like. So here I've got carbon 14, which I told you all was unstable. It's one of the smaller nuclei that are actually unstable. What is going to happen is that this is going to convert into carbon, or rather nitrogen 14, and then we have a beta particle. So in this situation, an electron is emitted from the nucleus and a neutron will actually convert into a proton. So do you see how I have my atomic mass is the same? It's 14 here and it's 14 here with my new nucleus. The mass didn't change. Why? Because the beta particle has no mass. But what happened to my protons? I took one of the neutrons and converted it into a proton. So we went from 6 protons now to 7 protons. We didn't change the mass. We just took one of the neutrons and converted it. So let's look at what that would appear like in a nuclear equation. We have our carbon 14, which has 8 neutrons and 6 protons. We give off one of these things. The number here stays the same. This number increases. Why does it increase? Well, remember, if this is 6 here, this side also has to equal 6. And if you have a -1 here, you have to bump this number up to compensate for the -1. 7 plus -1 gives me the 6. Or we went from 8 neutrons to 7 neutrons, 6 protons now to 7 protons. We bumped it up. So let's look at this here. We've got potassium 42. We want to convert this, or we want to have this go through beta emission or a beta emitter. That means we're going to release an electron. And we want to figure out, well, what is the new nucleus? Okay. Well, if this is 42 here, my total on top needs to be 42. None of that's being occupied there. So the total mass of this new nucleus is 42. What happens down here? This is 19. So this also has to be 19. Well, there's a -1 here. So what I need to compensate for that -1 is another additional proton, or a 20. 20 is going to give us the symbol calcium. Okay, remember these two things coincide with each other. Let's do another one of these, beta emissions. Okay, I want you to do this one. So write the full nuclear equation for beta decay of cobalt 60. Okay, so for this one, we're starting with cobalt 60. We've got cobalt 60, and I'm gonna fill in its symbol, which is, or its atomic number rather, which is 27, just so I have that information there. So this is undergoing beta decay. So I'm giving off an electron. And again, I like to write mine first, just so it's sort of ordered out. So what remains needs to be, well, let's see, we've got 60 here and we're subtracting 0 here. So this whole side needs to equal 60, the top. So this has to have a mass of 60. This is 27 on the bottom. Remember, the total needs to be 27 on the bottom as well. So 27, there's a -1 here. So this actually will need to be 28, or we have converted one more proton. Look on our periodic chart. What is 28 going to be? It's the next guy up, or nickel. So this would be beta decay. Why not just for fun? Let's do the same thing, but let's do it for alpha decay. Okay, so we've got cobalt 60. And instead of beta decay, it's going to undergo alpha decay. So why don't you see what you can get if you undergo a different type of decay? It's definitely not going to be nickel. Okay, so just changing this a little bit and saying instead of it undergoing alpha, we're going to go, or rather beta, we're going to do alpha decay. So if it's alpha decay, that means I need to give off a helium or 2 He. If this is 60, then this over here will need to be, I can add, I swear, 56. 56 plus 4 gives us 60. This is 27. This needs to be 25. And then we just look up what our 25 is, and it's manganese. And manganese. Okay, any questions on either of those two as of right now? No? All right, we'll keep moving on. That. All right, so positron emission is where we give off a positron. And remember, a positron is sort of the antimatter of an electron, so it has no mass, but it has a positive charge. This is when we take a proton and we end up converting it into a neutron and ditching its charge. So the mass number of the new nucleus will be the same, but the atomic number in this case will decrease. So this will go from 25 to 24. In beta emission, the number, the atomic number increased. In positron emission, because it's the opposite, it will decrease. So 49, 49, but we go from 25 to 24. So let's do a positron. I've got one over here on our worksheet. Where are you? There you are. Beta decay. No, does it not do a positron? Okay, well, let's just go back to the slides. They don't give us an example. I really like that. Let's go back to this one that we've been sort of playing around with. So we've got cobalt 60. Let's say this undergoes positron emission. Okay, so we've done beta emission, we did alpha emission. Let's make this a positron emission. I'll give you all just, I don't know, a minute and a half to work on it. So we've got, is that a question? Did somebody have a question? Okay, so if we're going through positron emission, that means we've got our little electron symbol, no mass, but it's got a positive charge. So if that's the case, my mass should stay the same for my new nucleus. 27, this is positive, so this will need to be 26. 26 plus the 1 gives me the 27. So 26 will just be whatever comes before cobalt. In this case, it would be iron. Is this really a decay that happens? Probably not, but you know, just so that we can practice. All right. So then we have gamma radiation or gamma emission. Now, gamma emission, because it doesn't have any mass to it and it doesn't have any charge to it, it's not actually going to change what the nucleus is. It's just going to make it more stable. It's just releasing some of the energy from the nucleus. So a lot of times it'll be written, the previous one, or the unstable nucleus will be indicated with a little M symbol. So we'll say 99, and then we put this little M or cursive M, and that just says that this is unstable. It's got a lot of packed energy in it. If we undergo alpha, or rather, sorry, scratch that. If we undergo gamma, the nucleus will be the same, but we've ditched some of that excess energy. So now we don't write the M on the other side. That's as simple as that. So same nucleus, we just ditch the M to release the energy. And then we put the gamma ray. So here are all those things that we've talked about. So if we go through alpha emission, we have an alpha particle, we have a new element that has 4 less on its mass number and 2 less on its atomic number. Beta emission, we give off that electron, we have a new element and its mass number stays the same, but its atomic number increases by 1. Positron, we ditch a positive charge and we get the same number, but our atomic number goes down by 1. And then gamma ray will have the same nucleus, but it becomes stable. So that sort of sums up the last couple slides. All right, so what are we sitting at time-wise? 12:03. Yeah, we can talk a little bit about this. So how do we get a radioactive isotope in the first place? Well, a lot of times what will happen is a stable nucleus, so something that's kind of happy on its own, will get bombarded. It will get hit with another particle, and that particle will then make it radioactive. This process is called transmutation. It's called bombardment. So I've got a stable boron nucleus here, and it gets smacked really hard with an alpha particle. And when this happens, we get a new radioactive isotope. This one is specifically nitrogen-13, and then it happens to release a nucleus, or rather a neutron as well. So this is a little different in that our starting is we actually have 2 things. We're adding these together and we end up with 2 things. We don't always end up with 2 things. Sometimes you can have 2 on this side and 1 on this side. So if we look at this here, this says write a balanced nuclear equation for, so we wouldn't have this part, but we would say write the balanced nuclear equation for the bombardment. And when you hear the word bombardment, that means it's 2 things getting smacked together, of nickel-58 by a proton, which produces a radioactive isotope and an alpha particle. If we want to figure out what the radioactive isotope is, we've got to first write our formula or our equation. And so it said bombarded nickel-58. So here's my nickel-58. I write the 58 in the top, and then the 28 is in fact the atomic number of nickel. I bombarded it by a proton. And remember, this is a proton. Hydrogen is just a proton. So we put our hydrogen with our 1 and 1. And this produces our helium, right? Because it says it under 1 alpha particle. Hold on 1 second. Sorry about that. Okay, so this, when looking at this, this is a starting and this is a starting. We have one of the ending, or one of the results is that it's an alpha. We need to figure out the other thing. So how do we do that? Well, remember the top things need to equal each other. So in this case, it's 58 plus the 1. So this whole side has a value of 59. If that's 59, the other side also needs to equal 59. 4 of it is being occupied by the alpha, so that means that there is 55 for our mysterious isotope. Sorry, my daughter is talking to me. Okay. Other part of this is the atomic number. So I've got 28 here and I've got 1 here. I need to add those two together to give me a value of 29. So this means over here, this whole side needs to equal 29. 2 of them are being occupied by the helium. So 29, 28, 27. This should be 27. And then we just look up what 27 is, and it is cobalt. Okay, so this is a little bit different than the previous ones in that you have to do a little more work adding those two together, but it's not that much more work, right? But just make sure you've got the totals on both sides. Tops equal each other, bottoms equal each other, and you should be good. I kind of like doing these. I think they're kind of fun. So let's clear this out so we can see the next slide. Okay, so it goes through that whole process and we ended up with the cobalt. So I want you to do this one. And know that you don't necessarily get this, right? Sometimes you're only given the word part. So what radioactive isotope is produced when a neutron bombards TC98, releasing an alpha particle? Okay, so it did give it to you. So write this out for now, but don't always assume you're going to get that. And I want you to tell me what the mystery isotope is. Okay, so just make sure you're totaling everything up. So on this side, the top value, 98 and 1 means that I have a value of 99. So this should also be a value of 99. My mystery isotope will have an atomic mass of 99 minus the 4 is 95. You good with that number? Where that number's coming from? A couple ladies I can see. Head shake, okay. Bottom, I've got 43 and 0. So 43 is the total for the bottom. So on this side, we also have to have a total of 43. 2 of them are being occupied by the alpha particle. So 43, 42, 41, 41. Now we've got to figure out what is 41. Just look at our periodic chart. Nebidium, I think is the name of that, NB, Nebidium. So there is our mystery isotope. think nuclear chemistry sometimes scares people a little bit when they hear that chapter is coming around. It's like, oh, what are we going to do? It's not too bad. As long as you know what your particles are, it's just a matter of adding and subtracting. Go through what they had. There it is. Same thing. Okay, so I think we'll stop for there. We'll stop there today. We'll do some more practice. We're not going to do the Geiger counter stuff yet. We'll do some more practice on the bombardment next time. So if you can get that lab either printed out or just have it readily available so we can work on it. Where did you go? This lab right here, right? So have this available for you so that we can sort of chip away at it and get some of your lab homework done for the weekend. Again, remember it is nestled in the lab section of Moodle somewhere. All right, we'll see it right here. Okay, it's the one that looks different. So that's your nuclear radiation. That's the part 2. There is one that you have to do in your lab as well. Okay. So we'll stop there. If you guys have any questions, hang out. I think there was 1 or 2 people that said they wanted to chat after class through email. So stay around. If you don't need me, get out of here and enjoy. I just stepped outside for a hot second. It is so nice outside. So enjoy the weather. Bye, everyone.